Okay, sorry that last video cut off at an inopportune moment, so pick up where we left off. We finished off the derivatives, and then what happened is we used the coefficients, which aren't listed very nicely here, but we decided that those circled values here on the left actually end up being really nice looking factorials: 1 factorial, 2 factorial, 3 factorial, 24 factorial, respectively. And so let's see if we can get that to play out. Yep, there they are. Bam, 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 bam. And if I pause this real fast and let you check it out, we get cancellations of all those factorials. And 1 over 1 minus x is this 1 plus x squared on up to x. It's just x to the n. And so a very nice looking function. In fact, it becomes one of our key series functions that we want to have memorized so that we can manipulate it in the event that it's a Maclaurin series centered at 0. Then we can manipulate it using various algebraic substitutions, operations. We even do integrals and derivatives to come up with other series. And so that's how it works out. And I don't know why that's overriding in weird ways. Anyhow, next in line, so we did this long division stuff, which is pretty cool. I'm going to jump way out here to the end here, see if I can find the next place. We did some of these series. The one I want to do right now is, let's talk about 1 over 1 minus x, just ever so briefly. That's x to the n. If we do 1 over 1 minus 2x, we're interested in what effect that has algebraically on the difference between that and 1 over 1 minus x. And if you can think about it, we're doubling x in that situation. What does that do to the graph in that situation? And that happens too, if you remember. If you double x, we get something that's half as wide. It actually takes and compresses it. So here we go. I got to put this back in. So here's 1 over 1 minus 2x. All worked out. We're going to do the ratio test. Sorry, it's kind of jumping back and forth on me. I've had some issues with technology today. But 1 over 1 minus x, if we do 1 over 1 minus 2x here in example 6, 2x goes in for each of those x's, squared, cubed, etc. And then it's 2x to the n. And if we want the interval of convergence for that particular series, we're going to do the ratio test. And here it comes. The ratio test to infinity, do the n plus 1 over the nth term, absolute values, and then less than 1 is required for convergence. And then you set it in the right form, where you have center of 0 and radius of 1/2. And then we have to test the upper and lower bounds. Now, think back to what it was for when we did 1 over 1 minus x. That interval of convergence was -1 to 1. Now, it's important to remember that, because our now half as wide compressed function, horizontally compressed function, I'm imagining what that might have as far as the interval of convergence. It looks like it's from -1/2 to 1/2. It looks also compressed. And if all is perfect and well, it should be from -1/2 to 1/2, not including -1/2 and 1/2. So we should have parentheses. And that is the truth. If I put in -1/2, I have -1 to the n. That's an oscillation issue, so diverges by oscillation. And then if we do 1/2, plug that in a bit mentally, you can see that you get 1 to the n, that diverges to infinity, because if you do the nth term test, it goes to infinity, and that is not 0. So the cool thing about this is, if you take the function and you horizontally compress that function, then your convergence, interval of convergence, will behave accordingly. All right, to the bottom. Next bit of business, we in class went ahead and tried to do a cool, 1 over 1 minus x, and then we converted that to 1 over 1 minus a negative x, so that we could do 1 over 1 plus x, and we figured that out. And then in all our cleverness, we thought, ooh, what if we did 1 over 1 plus 3 plus x, which would be equivalent to the 1 over 4 plus x? Would that work? So could I take my series for 1 over 1 plus x and replace all the x's with 3 plus x? We tried it. Didn't work. It gave us a function. We used the Pascal's triangle. I mean, we tried all kinds of stuff. Good old Blaze could not come through in that situation. But one of these, and when you have these series that are rational functions, you can always do long division to produce the series itself, so long as you can pick up the pattern. Now, our little function, let's work it out here. The center in this case, I put in there not 0. The issue is when the center suddenly becomes not 0, that is, you're adding or subtracting some value to your x term within the function itself, that's going to cause problems. We need centers of 0 to do manipulations to mess with our intervals and be able to come up with new intervals. This is not the case in what we're doing here. So we're going to try long division, and it's not a fun long division. 4 goes into 1/4 times, and then if you multiply through by 1/4 and change the sign and add down, here we are. 4 goes into negative 1/4. Is that like negative 1/16 x times? Multiply through, add down, and now we have negative 1/16 x squared. And then we get the next one, and it's 1/64. And if you're lucky, you're seeing a pattern. And this particular pattern is 1/4 to the n, x to the n. The hard part about long division like this is you do have to look out for a pattern in how those fractions or other coefficients are generated. So you have to notice that pattern in order to come up with the nth term. And therefore we can do a series and then do the ratio test with that series accordingly. And I'm just going through, letting this go ahead and play out. You can play it out at your own speed, but the n plus 1th term over n, if you carefully swap places, those negative exponents, if you're not sure how this happens, you can actually swap those, put one on top and the other on the bottom. So that means you have a 1 degree higher of the 4s on the bottom, and x is 1 degree higher on top. And so when you cancel all those out, you get x over 4, and you have absolute values. If you're having trouble with this, just go ahead and do same bases. When you're dividing them, you subtract the exponents. Just go in and subtract those exponents. Figure out where the 4 and the x go. And then we set it less than 1 because we want it to converge. And multiply both sides by 4 to get a radius of 4, center 0. The next thing is to test those endpoints into our original function. And if you do a little simplifying, one of the things, if you have a negative to an nth power, you want to factor that out to a negative 1 to the nth of its own. Often you can do things like, hey, let's cancel those 4 to the n's. And then negative 1 to the n divided, or as a divergence by oscillation. Put in 4, we get 1 to the n. That's diverges because it goes to infinity if you add a bunch of 1s. So again, we're looking at parentheses, negative 4 to 4, not inclusive. And pretty slick. So that one's a long division. That ends up being a handy tool. Plus, remember, we can graph these and see how they fit as well. And that's a great comparison. We did that in class as well. That closes out the big stuff, the big ideas in 11.4. We'll do some more problems tomorrow to kind of hash out some of the details, but enjoy.